Hello everybody, this is the third video clip of our chapter 3 for the cost calculus for business 2. Okay, previously what you have learned is about the function of, if we given a function of two or more than two variables, then what you can find is a partial derivative with respect to each of the variable. For example, if you look at a partial derivative with respect to x, you may use this notation dz by dx, df by dx, but instead of straight d you use a curve so that you indicate that your function depends on more than one variable. So, okay, or you use a subscript f subscript x, and it is determined by the limit as your h goes to 0 of f of x plus hy minus f of xy over h. So this means that the only thing that change is the x variable, your y held fixed. Okay, so to do, as you did in the problem, when you find the derivative with respect to x, you are going to regard your y as a constant. Okay, only the x that is a variable in that consideration, and then you just find the derivative as usual. On the other hand, if you're finding a derivative with respect to y, then your x will be fixed and only the y that will change. Okay, so this one, your y is changed, and your x, you are going to regard it as a constant, okay, in the context, and then you find a derivative with respect to the variable y alone. All right, today what we are going to do is that we are going to do some kind of approximation. Instead of using the limit, okay, we can say that f sub x can be approximated by f of x plus h and y minus f of xy over h. Okay, in particular, your h usually it is a 1. Okay, usually it is a 1, so it becomes f of x plus 1 y minus f of xy. Okay, or you can say that f of x plus 1 y can be approximated by, this is multiplied by 1, right? But actually there's nothing, is it? So it can be order different between here. Okay, let me just conclude this one first, that the difference between your f of x plus 1 and x, okay, can be approximated by f sub x at a particular point xy. Okay, on the other hand, if you talk about f sub y, f of x and y plus 1, okay, minus f of xy, so it's a difference between a function value when your y is added by 1 and with y, so it is approximated by f sub y at a particular point xy. Okay, all right, so these are called marginal. These are called marginal because the change is only changed by 1 unit, you see, on each of the x or the y. So this one is called a marginal. So what we are going to emphasize on here is a marginal cost. Okay, actually you have learned before in your calculus 1 as well about the marginal cost, but this one, it is a marginal cost in terms of two variable or more than two variables function. Okay, so suppose that a manufacturer produces x units of x and y units of a capital Y, then a total cost C of these units is a function of x and y, which is usually called a joint cost function. So such a function can be represented by C equals to f of xy. So of course, a derivative of C with respect to x, this one we'll call a marginal cost with respect to x. Okay, and this one, as we did here before, instead of f we use a small c, right? C sub x or c sub y. Then we know that this one can be a good approximation of your c of x plus 1 y minus c of xy. You see, so it's a cost that may either increasing or decreasing depends on the sign, right? After you do, if it is positive, then it means that the cost is increasing. If it is negative, then it means that the cost is decreasing. Okay, so this one, the derivative of c with respect to x, it is a good approximation of the cost of produce one more unit of x, but your y fixed to be the same. Okay, and this one as well, this one a derivative of c with respect to y, which is a marginal cost with respect to the y. So it means that the change, it will be the change in y only, and your x remain the same. You see, so this one is a good approximation for the change in cost if your y produce one more from original. Okay, so and the previous one is the change in cost if your x produce one more than what we have at the beginning. Okay, for example, if you're talking about this one, a manufacturer have two types of skis. Okay, one thing is lightning and the alpine models, and the joint cost, okay, of producing x pairs of lightning and the y pairs of the alpine per week is given by 0.07x and 75x, 85y, and 6,000. So of course your C is expressed in dollar. You need to determine the marginal cost and interpret the result. So here, I mean, it is pretty straightforward. So this one is a marginal cost with respect to x. Okay, so the derivative will go directly to where your x is, but the rest right now they are a constant, right? So this one, the first one, derivative of 0.07 x squared become just 0.07 and 2x, right? This one, a derivative of 75x, it is 75 and 1, and the rest, because they are right now a constant with respect to x, so you have all 0. So here you have 0.14x and 75. And if you need to find the marginal cost with respect to y, okay, with respect to y, then it means that all these are now a constant, okay, with respect to y, and this one as well, it is of course already a constant. So only this one alone that your derivative will apply to. So it is 85 and 1, or is simply just 85. Okay, so let us try to interpret the results that we got. Okay, so here this is like I told you, the one of the typing version. Okay, so it will be the same thing, the marginal cost with respect to x and the marginal cost with respect to y. Let us try to interpret what it is. Okay, so this one means that the rate of increment, okay, the increasing the increment of the cost when your y is fixed. This one is very important. Okay, you need to write down this one, that your y is fixed, is higher with a higher value of x. Why is that? Because you have this factor 0.14 multiplied by x. So as your x increases, okay, as your x increases, your y stays still, then this one, of course, the cost will be increased, okay, by this increment. Okay, however, the rate of increment of the cost, if your x is fixed, is constant. You see, constant. So there's no variable here, so it's constant. I mean, at any level of production. So if your x is fixed, but you keep increasing your y more and more and more, okay, this increment of the production of your y still reflecting the increment of only 85 each. Okay, 85 each, always 85 each. So if you just plug in one of the fixed number x and y in there, okay, for example, if your x is 100 and your y is 50, but right now you have your x alone, then you obtain the result of 85. This is pretty important, okay, how you interpret it. It says that if you increase your x, okay, originally from 100 to one more 101, don't forget, right? This one, it is the good approximation of the what? A cost of 101 and 50 minus a cost of 150 standstill, right? Remember, as we just explained previously. So this means that even you look at 100, so it means that it need to increase from 100 to 101, but your y stands still, okay? So the cost, okay, will increase by approximately, okay, $85, okay, $85, okay. However, if you talk about the same at the same level of production, okay, originally your x for 100, your y for 50, and you just, you know, if we talk about this one is a good approximation of what? C of 100 fixed, but your 50 added by 1, okay, and the difference of 100 and the 50 originally, okay. So it means that if you increase your y from 50 to 51, okay, this one, even though you indicate at 50, but it need an increment of 1 unit from 50 to 51, and your y fixed, your x is fixed to be 100 always, then the increment or the increasing of the cost will be approximately $85. Very good. So this is how we interpret it, and these are very important because we will ask you to interpret the marginal cost always. Okay. Another application is also a marginal, but this one is so-called a marginal productivity. Okay. So the output of the product, of course, depends on many factors of production. One simplicity model is that, let us suppose that the output depends on the labor and the capital that you invest. Does that make sense? The labor, I mean the number of laborers that you can that can work for you, and the money that you can invest in. So if the function P, this one of course P stands for production, is in terms of F of L and K, your L should refer to, of course, a labor, right? This P is the output or production output, okay? When you can use the L units of labor and the K units of capital, okay, then this function is called a production function. Of course, I mean the PDL is a marginal productivity with respect to L, and the PDK is a marginal productivity with respect to K. And again, by the same old interpretation, this one is a good approximation of what? Of your P when your L increased by 1, okay, comparing with the P of LK, okay. So this one again, only the L that changed, and it changed by only 1 unit of L. And this one, it is a good approximation of your L and K plus 1 comparing to the original production P at LK. So here the only thing that changed is your K, and your L stands still, and the increment is only 1 unit in terms of K. Okay. So let's look at this example. Okay, let's look at this example. This one, you know that the manufacturer of the toy determine that the production function is capital P equals to square root of L and K. Okay, L is the number of labor hours per week, and your K is a capital. But this one, be careful. This one, 1 unit is hundreds of dollars per week. Okay, so and P of course is a production level in gross of the toy. You need to determine a marginal productivity functions and evaluate them when your L is 400, your K is 16, and interpret the result. So let me just rewrite this one in terms of, you know, L raised to the power 1/2, K raised to the power 1/2. Okay, so it means that the first thing that you may need to find is the marginal productivity with respect to a labor L. Okay, so it means that the variable is the L alone. Your K is a constant in this context, so your K go first, and the derivative go directly to your L raised to the power 1/2, which is 1/2 L raised to the power negative 1/2, or you can simplify it if you want, okay, to be a square root of k and 2 square root of L. All right, okay. How about the other one? If you are finding the dp dk, okay, on the same token, now your k is a variable, your L raised to the power 1/2 right now is a constant, so we write down it first, and then this one kick it down 1/2, and then k raised to the power negative 1/2, or you can say square root of L to square root of k. All right, okay. So what does this mean? This kind of fractions, what does this mean? Okay, so here is the increment in terms of L, right? And then your L becomes your bottom, and your k is fixed. You see, your k is fixed, and usually the increment, it means you increase your L by like about 1 unit. So it means that if your L is higher, then this L becomes the fraction to be divided by the fixed capital K. Okay, so the change depends on like the higher of the L. Okay, and this one as well, the change of K depends on the higher the level of your K at the origin. Okay, so let us look at the typing version and then also the interpretation. Okay, so this one, the rate of increment of the output P whenever your K is fixed is lower, right? Because it depends on the value of L. If your L getting higher and higher, this one will be, the increment will be lower. And the same token, if your L is fixed, because your top is fixed, but your bottom getting higher, then again the rate of increment, the rate of change of the production with respect to K when your L is fixed will be lower as your K getting higher and higher. All right. So what if you need to evaluate L at 400 and K at 16? So you just simply do a plug-in, right? Here is your K, there's your, here is your L, there's your K, okay? So you just plug in your K to be 16, you see here, and your L to be 400 there, okay? And then you taking a square root. All right, so the one on the top is 4, the one on the bottom you got a 20, so you're 4 over 20 and then divided by 2 again, so you have 0.1, okay, which is positive. So what does this mean? It means that if you don't forget that this one is a what? Let me just write down again. It is a good approximation of difference of production as you increase your L by 1 unit, okay, and your K is fixed to be 16, comparing with the original production that your L is 400 and your K is 16. All right, so this one, if you increase your L, okay, the labor hour from 400 hours to be 401 hour, but your capital is fixed to be 16 unit, the increment or the increasing in output is approximately by 0.1 gross. Okay. However, if you did another way around, your L is fixed to be 400, but your K increasing by 1 unit from 16. So this one is a good approximation for production comparison between this one with increment of your K by 1 and the original production of 400, L and 16 of K. So you just doing the same thing, but just switching between the row between the top and the bottom from the previous one, and you got 2.5, okay, 2.5. So what does this mean? It means that if you increase your K from 16 to 17, you see, from 16 to 17 unit, but your L, the labor keep into 400, the increasing in output will be approximately 2.5 gross. Okay, so this one, don't forget that the increment, even though you see that it increased by 1, but 1 unit of capital, it is what? 1 unit of capital is actually $100. Okay, so sometimes this one, don't forget that it is the same as increase by $100. Okay, so read it carefully when you do with a word problem. Okay, so what is this two thing indicates or tells you? So I mean, if you can hire more labor, then the only increment in production will be only 0.1 gross. But if you can invest more by 1 unit of your capital or $100, it will increase by 2.5 gross. So it depends on, I mean, if you have more money, you may say that, hey, I'll do this way so that I'll still keep the labor to be the same, and then I have more, increment in production out of it. But if you say that, hey, I don't have money, but I still have more people, then we do it this way. So this derivative with respect to of the P with respect to L and the derivative of the P with respect to K will give you, roughly speaking, what you are going to do with your business. Okay. Now let's look at this one. This one is another kind of example. Okay, so they don't tell you exactly what they want. For example, they don't tell you like directly that they want a marginal of something, but this one, let's read. It says a weekly output. So this one is about the what? The production, right? Of a certain plant is given by this function q of xy equals to 1200x and 500y x squared y x cubed minus y squared, where of course the x is a number of skilled workers and the y is a number of unskilled workers employed at the plant. Currently, the workforce consists of 30, which is x, right, skilled worker, and more of unskilled worker. Okay, it is 60. Estimate the change. Okay, estimate the change in the week output. So the change in the week output is the change in Q, right? That will result from additional one more skilled. So which one that there is added? So this is from x to x plus 1, right? Worker. If the number of unskilled worker is unchanged, okay, even though it's not that direct, they also give you some kind of direct message that, hey, your y unchanged, you see, but your x changed from x to x plus 1. So what is that good estimate of your q, okay, of the difference of the q? So don't forget that the good approximation that you need for the q of x plus 1 and y minus q of xy, it is a q sub x. So it is a marginal output, right? A marginal output with respect to x. So this one, you already given your q. So can you find the q sub x, okay, a derivative with respect to x? So here it is 1200, okay, and the derivative go directly to your x, which becomes 1. This one, there's no x right there, so a derivative is 0 because here is a constant, right, in this context. How about this one? Your y is a constant, and a derivative go directly to your x squared, which will give you 2x. This one is already in terms of x alone, so you got 3x squared. This one is again a constant in this context, so you have a negative 0. So totally you got 1200 and 2xy and 3x squared. Okay, but right now at which level that you are going to estimate the change? Right now the level is your x is 30, your y is 60, so you are going to do the change in 30 plus 1, 60, minus 30 and 60 for your x and y. it will be a derivative with respect to x of q when your x is 30, your y is 60. This was pretty one of the most confusing, okay, because here is your x and y, okay, so here must be x and y. You don't use this one, all right, okay. So you already have everything right here, and this one, let me just use the approximation sign, okay. So as your x is 30, your y is 60, so you are going to have 12 hundredths and 2 30, 60 minus 3 of 30 square, okay. If you want, this one can be your good final answer, all right, but however you may need to calculate a little bit, okay. So this one it is what, 36 hundredths, right? So and this one it is 27 hundredths, isn't it, with a negative sign. So you got what, 9 hundredths and 12, so you have 21, I guess, okay. So you need to check my calculation always, okay. I usually calculate a wrong number, but this one I guess is correct. So here the change in weekly output, okay, in weekly output is going to be increased by, so if you increase the skilled worker by 1 person, okay, by 1 more from originally 30 and keep unskilled to be 60, then the output will increase, of course, by 20 hundredths unit, okay. What you may what we would like you to do is that if on the other way around, if you increase your unskilled by 1 more from 60 and keep the skill to be the same as 30, then the output will, we still don't know whether it increase or decrease by how many unit, okay. So if it is positive, of course it will be increasing. If it is negative, then it will be decreasing, okay. So just use the same function q over there and then do this problem instead, okay. This one we increase unskilled by 1 more and keep the skill to be 30. What will happen to your output level? What is the change? All right. So we are going to stop our video clip right here at this point first, and we will see you later on. Bye bye.